This video is for the revision of equilibria SL. Okay, this chapter is going to cover reversible reactions. What is a reversible reaction? It is one that can proceed both ways, both directions. So for example, here, if I have SO2 and oxygen, SO2 and oxygen will form SO3, but at the same time, SO3 will also form SO2 and oxygen. So the reaction is going both directions. These are two graphs to show the difference between a reversible or non-reversible reaction. So a normal reaction is not reversible. We'll see that the reactant's concentration will fall to 0 at some point, and at that point, the product will have no changes in concentration anymore. That is when the reaction completed. But as for a reversible reaction, it will reach a certain dynamic equilibrium. And at that point, the rate of the forward reaction and the reverse reaction is the same. So looking at this graph, the reactants drop in its concentration and the products increase in its concentration. But at some point, it's constant. The products are constant and the reactants are constant. And at this point, you'll see that both the reactants and the products never reach 0. So there is reactants and products at this point. So at this time is when it reached an equilibrium. We call that dynamic equilibrium. That is the time where the rate of the forward reaction is equal to the rate of the reverse reaction. It looks as if there's no reaction, nothing's going on, but actually both ways, the reactions are still going both ways. Okay, the concentration doesn't change anymore, so it's already stabilized here, and that's the point where it reached dynamic equilibrium. Everything may appear stationary, but they're actually not. They're just moving both ways. Okay, this equilibrium can only occur under closed system. What does this closed system mean? So if we don't add moles of reactants or products, if we don't change the temperature, if we don't change the pressure, that is a closed system. We don't change its conditions. We are going to calculate Kc, or reaction quotient. So the way to calculate Kc and reaction quotient is actually the same method, just that for Kc, it's when the reaction is at equilibrium, at dynamic equilibrium, while the reaction quotient is at any time of the reaction. So it might not have reached equilibrium yet. Okay, so this quotient will help us gauge whether that reaction is going to move more to the forward reaction or more towards the reverse reaction. So this helps us gauge which direction is the reaction going to go. Let's look at this example. 2 immiscible solutions of iodine in water. So water is this layer here, and tetrachloromethane, so CCl4 at the top layer here. So iodine is in both of these solvents. They are mixed together and the reaction quotient measure before shaking. Okay, so if the Kc, this is at equilibrium for the 2 solutions at a given temperature is 650, so this is at equilibrium, and the value of the quotient is 800, so it's too high, obviously. Which way will iodine pass? So we need to lower this 800, we need to lower it to 650. So at this moment, there's too much in here, that's why the value is high. So we need some of the iodine from CCl4 to move towards the aqueous layer, so that 800 would drop to 650. So which direction is the iodine moving? So it's going to move towards the aqueous layer. Okay, if a system is already in equilibrium and we make a change to it, it will try to oppose that change so that it will form a new equilibrium. Okay, so what is this equilibrium? Again, I'll remind you, so that equilibrium means that the rate of the forward and the reverse reaction, so the rate, remember that is the rate, is equal, and it looks like there's no more changes in the concentration. The concentration has become constant at that point, then that is dynamic equilibrium. So at that point, if you make a change, it will try to oppose that change. Let's say this equation this reaction is already at equilibrium, at its dynamic equilibrium. So that's when the rate of forward and reverse reaction is the same, and there's no more changes in the concentration of Fe3 plus, SCN negative, Fe, SCN2 plus. So they all have constant concentration at that point. And suddenly I were to add some FeCl3. So isn't that Fe3 plus? So if I were to disturb the equilibrium, so there's too much of Fe3 plus, what the reaction will do is that it will try to oppose that change by shifting to the right. What do I mean by shift to the right? It means that Fe3 plus and SCN minus will join so that it will form more FeSCN2 plus. So that's what I meant by shifting to the right. Next example, pressure. So pressure will only affect reactions that are gases. So if I increase the pressure of a certain reaction that's already at equilibrium, it will try to oppose that change, and it will favor the side with fewer moles of gas because it wants to reduce the pressure again. Okay, on the other hand, if I decrease the pressure, so it will try to increase that pressure, it will try to oppose the change. So it will move towards the side that has more moles of gas so that the pressure will increase again. So for example, if that SO2 and oxygen and SO3 is already at equilibrium, if I were to increase the pressure, it will try to go to the side where there's fewer moles of gas. So it will shift to the right because there's 2 moles of gas on the right and there is 3 moles of gas on the left. What if I were to increase or decrease the pressure for this equation here? 2Hi decomposed to H2 and I2. So there won't be any shifting to the right or left if I were to increase or decrease the pressure for this reaction because there's no difference in the number of moles of gas on both sides. So it wouldn't shift to either side. Okay, if a reaction is already at equilibrium and I change its temperature, if I increase the temperature, it will try to decrease the temperature. How? By going towards the side that is endothermic, so that is cooler. If I decrease the temperature, it will try to increase the temperature by going to the side that is exothermic so that it's hotter in there. So this reaction is an exothermic reaction. So if I want to get more SO3, so I want it to shift to the right. In order for it to shift to the right, I need it to favor the exothermic reaction. I would decrease the temperature. So if I cool this down, it will favor the exothermic side of the reaction. Then it will shift to the right. I'm going to get more SO3 yield. What happens if you add a catalyst to a reaction that's already at equilibrium? So there's no effect on the position, so it won't shift left nor right, but it will increase the rate of reaction. So it will increase the rate of the forward and the rate of the reverse reaction just as much. So it will just reach equilibrium at a faster rate. So a catalyst is very useful in increasing the rate of reaction for reactions which are exothermic, because reactions which are exothermic, if you were to increase the temperature to speed up the reaction, it is going to favor the side that is endothermic, so you will get less yield just because you want your reaction to increase in its rate. So that wouldn't be something we want. So we do want it to shift to the right and favor the side of the yield, but we also want it to be fast. So we wouldn't increase the temperature too much. Instead, we add a catalyst to help this reaction to speed up. Let's see how do we calculate the Kc of a reaction by using this R.I.C.E table. So that's reaction, the equation, initial, so initial moles, change, and at equilibrium. Okay, let's read the question. 1 mole of ethanoic acid react with 1 mole of ethanol. So I have 1 mole and 1 mole. When equilibrium is reached, it is found that 2/3 of the acid has reacted. So that's the change. Calculate the value of Kc. So those are the information that we had from the question. Now we're going to fill in those that we don't have from the question. So it didn't mention that there was any ester, and it didn't mention that there was any water. Okay, so if 2/3 a mole have reacted, 2/3 a mole of acid has reacted, and we know that this is 1:1 from the equation. So if 2/3 a mole of acid, it's going to react with 2/3 moles of ethanol here. And it's going to form 2/3 moles of ester and 2/3 moles of water. How do I know that? Because 1:1:1 and 1 according to the equation here. So this change, the ratio must follow your equation. So if here were to be, for example, 2, then here would be 4/3. That's how it works. Okay, so I put it back to 2/3 here. So if I have 1 mole of ethanoic acid and 2/3 have reacted, so 1/3 a mole is left behind. Same goes for alcohol. If I had 1 mole in the beginning and 2/3 a mole have reacted, so 1/3 is left behind. And if 2/3 of ester is formed and initially there was none, so 2/3 here. Okay, if originally there's a value here, say 1, then this would be 1 plus 2/3. That's how it works. Okay, I put it back to 2/3 here. And initially there is 0 water and it formed 2/3 mole of water, so 2/3 as well. Now we can calculate what is our Kc. So Kc equals to CH3, the ester, COOC2H5. So all of them raised to the power of 1 only, because there is no 2 moles anywhere. If there's 2 here, then 2 here. But since there's nothing there, so no 2 moles here. So therefore, 2/3 times 2/3 over 1/3 and 1/3. The answer is 4. And for this case, there's no unit because this would be in mole per dm cube, mole per dm cube, mole per dm cube, mole per dm cube. So they got cancelled out. Now let's try one where the ratio is not all 1:1. So there's 2Q here. And we write we draw the R.I.C.E table here as well. Let's pick up what we have from the question. 1 mole of P and 1 mole of Q are mixed. Once equilibrium has been achieved, 0.6 moles of P are present. 0.6 are present. How many moles of QRS are present? If the container is 1 dm cube, calculate the Kc as well. Let's fill in the rest of the values that are not from the question. So there's no R, no S at the beginning. And since there's 1 mole of P at the beginning and in the end there is 0.6, so I know that the change is 0.4. And this change has to be according to the ratio of the stoichiometry. So we know that 1:2:1:1 here. So 0.4 is to 0.8 is to 0.4 is to 0.4. So if I had 1 mole of Q at the beginning and the change is 0.8, so in the end I would have 0.2. I have no R initially, and the change is 0.4, so now I have 0.4. Same goes for S. The Kc expression, R, S, P, and then Q would need to be squared for this 2 moles here. So let's fill in the values. Keep in mind that these are supposed to be concentration values, not mole values. That is why they gave you the dm cube here. So I fill in the value here, 0.4, 0.4 moles in a dm cube, and 0.6, and 0.2, remember to square it. So mole per dm cube can be cut off here, can be cut off here and just the one here. So there's still one more mole per dm cube, and I'm going to bring it up so it becomes per mole and dm cube. Okay, if your question is in mass, you do need to change it to moles first, because equations, this reaction, equations are always in moles, and we follow the ratio of the stoichiometry equation here. So all this needs to be converted to the number of moles first. So the mass, I divide the MR for the carboxylic acid. So initially there's 0.1, and the alcohol, there is 0.13. And as for the ester, there is 0.05. Let's find out the change for the carboxylic acid, because they gave us the value at equilibrium. So the change, I'll add that here. So take 0.1 minus 0.04. We know that the ratio here has to be according to the equation. So it's 1:1:1:1, so 0.06 is the same for all. So the reactants become less over time, so minus, so 0.07 here. And this one, the products became more over time, so 0.11 and 0.06. So we can calculate the Kc down here. So I'm going to fill in the values. Remember, I told you it has to be the concentration value, and I only have moles here, but no worries. They're all in the same container, so they have the same volume. So I would say it's 0.06. Let me put that in order. So 0.11 over V, we don't know the volume, and 0.06 over V, and 0.04 over V, and 0.07 over V. So all the V can be cut off, and this will end up without a unit as well. So I have the answer without a unit. Do keep in mind that in the IBDP syllabus, you do need to discuss the compromise in Haber and contact process. So it's not only limited to the Le Chatelier's principle, but also the compromise when it's done industrially.